All right, my name is Rex Parsons. I'm a PhD student at QUT, and I'll be chairing this session. First up, we'll be hearing from Dan Van about probabilistic programming with PyMC. Do you want to share your screen, Dan?
Sure, thank you. Can you see my screen? All right.
Yeah.
Hi, everyone. My name is Dan, and I'm a PhD candidate at Monash University. I'm also working as a data scientist at Junction Control. So I use PyMC in both of my work in academic and research, and also in my work in the company. And today I will give an introduction about probabilistic programming in Python using PyMC. And there's a note here, I might be a bit biased for this because I'm also a contributor to PyMC, and it's one of the most popular library in Python for Bayesian inference and modeling. So let's start. So a bit review on this Bayesian terminology. So from the Bay formula, which is the conditional probability of A given B, on the above equation here, we translate it into Bayesian terminology, where we have the conditional probability of the theta, which is the parameter that we want to estimate, given the data y will equal to the probability of y given the theta multiplied with the probability of theta divided to py. So the p theta here is actually in Bayesian term, they call it the prior, which is our prior knowledge of the parameter before we see the data. And the py given theta here is the likelihood, which is our observation. And the denominator here is some constant that we normally calculate using the integral here, but it's normally very difficult to calculate. So we use some sampling approach for that. And recently we have MCMC, multi-Carlo Markov chain sampling for that. Anyway, the idea here is we have our prior on the parameter, and then after we've seen the data, we update our parameters. So we have this posterior distribution of the theta parameter given the data we see it. All right. So that is the idea of Bayesian approach. And in the talk, I will show you how to implement all these, the set of the prior and likelihood, and to view the posterior distribution using a simple example, using a linear regression example. All right. So why we need this to use Bayesian modeling? So here is a couple of reasons. Is for the interpretability, and it helps to quantify the uncertainty, because we have the distribution of posterior for parameters. And also the important thing is have to input the prior knowledge in our model, and it's important, especially in some industry where we know that, for example, that parameter had to be positive, for example. So, or in my work in my research, or travel time and travel cost, people will have a negative for that, for example. And it also have flexible and suitable for many applications. And recently it can be scalable as well, as it can integrate with GPU, for example. So why PyMC? So in Python, they have an ecosystem. So the core here, we have the Python, and the first layer here is we have NumPy is for numeric computing. Then we have Jupyter Notebook, we have Cython, and from the first layer here, we have the second layer built up, like for example, Pandas extension with NumPy that we can do data analysis. We have Matplotlib for data visualization, and also other library as well. And the third layer here, we have skit-learn for machine learning. If you do machine learning, we have start model here for doing statistical inference, and network H for network analysis. And you can see we have PyMC here for probabilistic programming, and also others library as well. So the Python ecosystem is quite mature, especially if we're doing data analysis and machine learning stuff. So for PyMC, recently we have released the version 4 just a couple of months ago, and now they have the JAX backend, and it supports GPU. So and it have a lot of feature and improvement for sampling as well. Right? So let's start with an example. So for today, I will use a famous combat quartet, which is a group of 4 data sets that have identical descriptive statistics. So you see that this 4 data set, they have the similar mean, standard deviation, and correlation. And the interesting data set we will look into that specifically is the first data set here, because it have a linear regression here, but it also have some outlier here. So at the previous persons in the previous presentation mentioned about the data is not normal, right? Outside. So here we very good example. We have some outlier in our data set. So let's go to that data set. So for this data set, I plotted in here, as you can see, the X and Y axis here, and we will use ordinary least square fit, and for that we will use a simple function in NumPy polyfit, and our model will something like y equal ax plus b. And if we using just polyfit in NumPy, we will have the slope is around this number, 0.5 something here, 0.4 something, and the slope is 3 point something here. So this can see that this line is not perfect because it affected by outlier here, right? So so that's why we need to use robust linear regression, and there are several approaches for doing robust linear regression. I will not mention here, but a simple way is we just remove the outlier and then we fit the other data set. So if we do that, we just remove the outlier and then we fit the left of the data set using just polyfit in NumPy. So we will have this our robust regression line, this one, and we will have this updated slope and intercept here. So this is the way we do it in like frequencies approach, right? And so how we can do the same thing in Bayesian approach. So this can be performed easily using PyMC. So if you remember last time we talked about the prior, the livelihoods, and the posterior. So in PyMC we can define just easily the PM here means PyMC shortcut name for PyMC. So we will what we do is we will define a model, right? And then in that we will first we need to define the prior. So in linear regression we will have our prior for the slope mean A and the intercept B, and then we have the standard deviation for that. And after that, we can define our livelihoods, which the mean is equal to AX plus B. And then we have a standard deviation using sigma. And we input the observed Y here for that. And after that, we can sampling the posteriors. And here, for example, I will sample 2000 sample for that. And the default of this sampling methods for MCMC using NUS, but we can also include other sampling methods like Gibbs or Metropolis, etc. And the model we're doing is something like that. We have Y equal to normal, X plus B, and with standard deviation is sigma here, and you can also visualize the model here as well. So what is the result? So compared to the previous linear regression in NumPy and using PyMC, you can see they have nearly similar result. In here, if you see that the slope of A and the intercept B, they is similar. So what is the difference? Why we need to use PyMC or Bayesian approach? Because we can have a whole distribution of the parameter A and B. So the parameter we show here is actually the mean value of that, but actually is in reality it is a distribution. So here is all the line that we have for different kind of A and B value for Bayesian inference, and you can see that it also affected by the outlier, right? And also we can see the distribution for the intercept and for the slope A and the intercept B, and also the standard deviation sigma here as well. So here we can see that we have some distribution, the whole distribution, not a point estimate like the NumPy case. So what about the robust linear regression in Bayesian ways? So we will do the same process, right? We will set the priors for that, but now instead the observation here, before we assume that it is normal, the data in normal distribution, but now we need to use the student T distribution, because student T distribution it looks like similar to the normal distribution, but it have a long tail, right? And this long tail can accommodate for outlier, which is our data set have outlier. So student T, they have 3 parameters, right? They have the mean, they have standard deviations, and then they have the new here. So that's why we also in the prior here we can also need to set the prior for new, and after that we do the same process. We can sampling it and visualize it. As the model now is look like that: y equals student T, A plus B, and we have one another parameter new here. So what is the result look like? So the result here is actually compared to the robust linear regression in NumPy or in frequentist approach, ordinary least square approach. We can see that it have almost similar result, and you can see that both of them it fit the data well and without effect by this outlier here. And the bonus of Bayesian approach, we have the whole distribution of all the parameters we have. This is the posterior distribution of all the parameters we have. So that gives you an idea about what makes sense, like how to use PyMC for a simple cases using linear regression. But there is a lot of example and application in PyMC, and you can check on the link I put it at the end of the reference here. So if you want to learn more about Bayesian approach in general, I would highly recommend to read this book, Statistical Rethinking, and from Richard Area here. He also have a very great resource course in YouTube that we can watch free, and then his book also ported in PyMC course, so you can also have a look at GitHub to how to implement all the code in PyMC. And for PyMC, there are several resources here and online book here that you can use. And for today presentation, this is the code I put it and to make the presentation, and you can go here to get the notebook that I prepare for today's section because here, and then you can download it and run it in your environment or in Google Colab, for example. So I think that is, I put some specific version here as well in case you want to replicate the environment as well. I will stop here and happy to answer any question. Thank you.
Awesome. Thanks very much. If there's any questions, just post them on Slack or in the chat. I think it's really cool that you got to contribute to PyMC, and I thought it'd be a cool thing to do as well. But I always see it as like a big daunting thing, contributing to a huge project like that. Could you talk about like what the barriers to contribution were for you, or how familiar were you with it before you even thought about contributing?
Yes. I think it the most difficult thing is the first PR you make, pull request you make to the open source project, and I spent quite a time to perform the first one, but after that you can get used to that. And the good thing about PyMC is they have a PyMC Discord and they have a community, and actually they have a monthly sprint that the PyMC developer, they can help the people to familiar with the source code and help them to like try to contribute. And in the PyMC project, you can see some issue, and they have labeled is a good for issue, for example. So if you start, you can start with something easier for that. So you learn the process for contributing to open source project first, and after that you can move to more complex thing or some module or some function that you interested in. Yeah.
Awesome, thanks very much. I haven't seen any other questions on, so we might just, in the interest of time, move on. Okay, so next up we have Owen Forbes talking about his amazing R package, Cluster VMA. Feel free to share, Owen.
Awesome, thank you so much, Rex. Are you looking at the right screen?
Yeah, all good.
Cool. Awesome, thank you. So hi everyone, my name is Owen, and I'm going to be taking you on a 5-minute whirlwind tour of how you can use Bayesian model averaging to combine results across multiple clustering algorithms. So often when we're looking at clustering problems, we'll find ourselves in a situation like this where we'll try out a few popular algorithms and they'll each tell us something similar but kind of different about the clustering structure in our data. So here you can see an example of k-means, hierarchical clustering, and Gaussian mixture model. And they're all broadly in agreement about the cluster structure, but here I've highlighted in yellow, these are the points that each of those algorithms disagrees about. So this puts us in a challenging situation to know what to do from this point onwards. Each of these algorithms will kind of be emphasizing different aspects of the clustering structure and will be sensitive to different parts of it. And one common traditional approach would be to just choose one best model out of these, but that can often be pretty arbitrary and an unclear choice. And when we make inferences based on just choosing one of those models, then those inferences aren't going to be calibrated for model-based uncertainty that arises when you're choosing between those candidate models. And when we lock ourselves into just one of those methods, we lose the insights that we could be gaining from the others about plausible structure. So why don't we combine them? There are some nice ways that are available in the existing literature to combine clustering solutions. And today I'm going to be talking to you about how using Bayesian model averaging is a really nice approach that offers a simple, flexible, and intuitive framework to combine these clustering solutions. So relative to other approaches, Bayesian model averaging has some really nice attractive features, including that you can weight the contribution of results from each model according to some measure of model quality or goodness of fit. And it gives us this intuitive framework where we get this probabilistic combination of results that can incorporate outputs from different algorithms. Another cool feature is that each input solution can have a different number of clusters in it. And importantly, it provides us with a framework where we can quantify this model-based uncertainty, and then downstream cluster-based inferences can be calibrated for that uncertainty and be made more robust. So I'll walk through what it looks like applying Bayesian model averaging. And in this context, we're looking at clustering young people based on resting state brain activity. So the basic premise of Bayesian model averaging is we're trying to estimate some quantity, get a posterior estimate for some quantity delta that has a consistent meaning across all the candidate models. And we're weighting the contribution of each model by the posterior model probability, or an estimate of it. So in this instance, delta for each clustering model will be the pairwise similarity matrix, and we'll use a weighting term W hat M to approximate the posterior model probability. So starting from these clustering solutions, the first step that we do is we represent them as a similarity matrix. And a similarity matrix is where each cell in these heat maps is talking about the pairwise probability that points I and J are clustered together. And then we weight each solution using a weighting term that I'll talk about next. And so you can see here, we're mixing algorithms which have hard allocation of just 1 or 0 probability and soft allocation from a Gaussian mixture model. So we need to approximate this posterior model probability in a way that doesn't depend on the specific clustering algorithm, and it doesn't depend on a likelihood being present in the model. So for instance, hierarchical clustering doesn't use a likelihood. And usually in the longer version of this talk, I'd talk about the rationale, but basically this is what we use. So we use a combination of 2 clustering internal validation indices, the Kalinsky-Harabash and the Sierra-Benny indices, and we combine them in this way. And then we normalize that weight and use it as an approximation for the posterior model probability. And you can find out details in our preprint, which I'll link at the end. So yeah, we get to this point where we've got each clustering solution represented as a similarity matrix with an associated weight estimating the posterior model probability. We find a weighted average cell-wise of those similarity matrices to get to what we call a consensus matrix. And then using that consensus matrix, we calculate our final cluster allocations using this step, which is pretty cool, called symmetric simplex matrix factorization. I won't go into detail given time, but basically it takes this consensus matrix n by n and factorizes it into 2 identical matrices, which each now contain the posterior probability of point I being allocated to the final cluster K. And here's what it looks like for the example that I introduced earlier. So here the points are scaled according to their uncertainty of allocation. And what's cool is you can see, as expected, you've got higher uncertainty at the kind of boundary regions between the well-defined clusters. And then you can take that uncertainty forward for cluster-based inferences. So I'm out of time, but just briefly, it might just seem like yet another method for combining clustering solutions, but it's got a bunch of cool features which other methods don't. It's intuitive and flexible, and we've written an R package that you can use to try it out for yourself. So you can go to this link, or I'll also drop it in the Slack. The preprint's here if you want to read the details, and there's also some on my Twitter. Thanks so much. Sorry for going a little bit over time. 5 minutes is really short.
Awesome. Thank you, Owen. Yeah, no questions for Owen, but I guess if you have some, please leave them in the thread, and no one can see them. Next up, we have Kylie Lang. The title, "What is old is young again." Kylie, are you happy to share screen?
Yes, hello. So I'm doing something completely, talking about something completely different. I'm a current PhD student, but the pathway that I've taken to get here is slightly different perhaps, and not exactly what I actively planned for when I first graduated. So I wanted to share my experiences, particularly for anyone who's considering whether postgraduate studies may be for them, or for those who are kind of new in your careers and wondering what the next 5, 10 or 20 years might look like. So to explain the title of my talk, I'm still in the habit of referring to the ECSS section as young statisticians, which was used to refer to kind of young in experience rather than age. So this is kind of the story of how I was once a young statistician many years ago, and now have regressed and have become young again. So my statistical timeline starts with my undergraduate back in the late 90s. I studied honours in statistics in 1999 and then went straight into the workforce. So my first job was an industry position for about 2 years, and then I moved to a statistical consultancy position in a university. That was my first, I guess, real statistical job. And I was in that position for about 7 years. So I suppose that somewhere through that period, I kind of aged out of being a young statistician and became whatever it is that comes next, middle-aged, I suppose. I then moved to a biostatistician role for a research group at Adelaide Uni. And I've been with them for almost 14 years now. So by last year, it was just over 20 years since I'd graduated, which I'm a bit worried makes me decidedly old-aged in this timeline. And then in the middle of last year, I started a PhD. So, you know, overnight, I once again became a young statistician again. And while I have, you know, potentially a different background than many people starting out a PhD, in a lot of aspects, I'm definitely facing new skills and new challenges in the same way as someone coming straight from undergrad. Over that same time period, my attitude towards doing a PhD definitely changed a lot as well. After honours, doing postgraduate study of any kind seemed rather intimidating, and I definitely wasn't interested. After a few years, I thought it would be a possibility if I felt I needed further qualifications just to be competitive for the types of jobs that I was interested in. Working in a university, you can sometimes feel like you're the only person, you know, in the world who doesn't have a PhD. So I thought, okay, maybe it'll be an inevitability one day. Over time, though, I did kind of gradually warm to the idea of it being something that could be, you know, of interest for other reasons. But I had quite a laundry list of conditions that I felt I had to meet before it would be the right call for me. However, in the last couple of years, it started to feel like it was a legitimate option that actually, you know, excited me rather than kind of terrified or felt like an obligation. And so when a potential opportunity came up a couple of years ago, I finally said yes. Now, of course, I'm only halfway through the PhD process so far, so I absolutely reserve the right to say this was all a terrible mistake and my attitude might completely change once again. So this might kind of come across as hypocritical now that I'm actually doing a PhD, but I feel like doing that wasn't necessary for me to build a fairly varied and enjoyable career that I could have quite happily continued with into the future. So looking back on those last 20 years, I think these are some of the things that have helped me kind of grow my career and build a competitive and attractive CV. So firstly, creating a network, I think, is quite important. Staying in touch with your undergrad peers through, LinkedIn, Twitter, getting involved in things like the Stats Society and the ECSS section, or the applied societies in the areas that you work in. Particularly for people working in large universities, and if you're the sole statistician within an area, perhaps reach out to other stats groups in your organisation and find out if there are any journal clubs or seminar series that they run that they would be willing to invite you along to. In both of my kind of stats roles so far, I've been the sole kind of statistician working in isolation, and those links, those informal links with other stats groups have been a real lifeline. Being proactive in your professional development, not only through formal things like workshops and conferences, but also doing your own kind of reading, working through textbooks, following journals in your own time is quite important. And one thing that I think has worked out really well for me is trying to say yes to all those extracurricular opportunities that come along. So I've had the chance to be on committees for the Stats Society, for organising conferences, for local grant funding bodies, ethics committees. I've done guest lecturing for stats topics and, do peer review for applied journals. So in all cases, they were things that people approached me about, people who knew me and knew a bit about my work. And so while I might have doubts about whether I was really qualified or appropriate to do this, you trust their judgment. If someone puts you up for something and you've got the scope to take it on, give it a go. So I guess my final message is that you don't have to have a PhD to have a career in statistics. But if you are thinking about it, even if it's many years since you were at uni, then it's not too late to look into it seriously. And I also feel that there's more reasons for doing a PhD now than I perhaps thought there were when I first graduated. I have a wider view now of what that can give me and how it can complement kind of the experiences that I have from my career already. So if anyone wants to chat further about any of these things, please do reach out, and I will leave it there. Thank you.
Awesome. Thank you, Kylie. All right, that's the end of our session. So I'm just going to pass back to Daniela, and we'll probably skip the break again.
Yes, I think so. Thank you very much, Greg. Thanks very much, Kyle, and everyone who presented exciting talks today. And yes, we are a bit late with the schedule, so I would propose us to start, and especially because the members from the panel are already here and they were here on time. So